Using the normal curve, we can find all sorts of probabilities, and when we talked about the empirical rule, we were pretty limited in terms of which values we could use. So to get to this point of where we want to look at other values that aren't a specific number of standard deviations away, we're going to use Geogebra. So to get started in Geogebra, what we're going to do is when you get to the website here, we're going to go to probability. And that will open up our bell-shaped curve, and you'll automatically be in the normal mode. So where you have this drop-down menu and we could change the distributions, we just want to stay at this original one of normal. So something we need to do to set up our curve is where the normal distribution is all about that mean and standard deviation, we need to edit those two values. So if we're using our Portland rainfall, we could edit the mean to be 40, so we can see our number line adjust there, and then that standard deviation of 8. So with that, it'll draw the curve very similar to how we did on our paper. So what we can do is improve on the values that we found when we used the empirical rule. So in part A, we had looked for this probability between two values, this probability of where 32 was the lower bound and 48 was the upper bound. And we can have these different scenarios of looking between two values. In part B, we looked above a certain value. In part C, we looked below a value. And it depends on in which direction you're shading of which of these three do you select in Geogebra. So remember, this first one works with the less than symbol. The double brackets are between two values, and then we have this last one that's for greater than. So we'll need to select one of these to decide which kind of area are we shading, and then we can type in our values to find the different probabilities. So let's say we want to find this probability between 32 and 48. If we go to our distribution in Geogebra, actually you can see the probabilities already typed in here, lower bound to 32, upper bound to 48, and we get out this 0.6827. So this 0.6827 is a more exact value compared to when we used our empirical rule, and that answer came out to about 68%. This is a more accurate answer that we're getting out. For more than or equal to 48, in Geogebra, more than or equal to, or this greater than, we need a shade to this right-hand side. So we just switch to this right-hand shading and adjust our value to be 48. And when you type into Geogebra, always make sure you hit enter so that all of the values adjust. And we see this 0.1587. And that's an improvement on what we found with the empirical rule, which was about 16%. So you can see they're close, and that's where empirical rule is great for a quick estimation, but it's not totally accurate. Less than or equal to 24, so this is going to shade to the left-hand side. And sorry, my screen's cutting it off, but it's just to the left of that double bracket. So shade to the left, and we need to adjust our value to be 24. Hit enter so everything adjusts, and we have this 0.0228, which is an improvement on that about 2.5% that we got out. And then part D was asking for this probability of being less than or equal to 56. So it's going to be an area to the left, and we just need to adjust our value to be 56. Hit enter, 0.9772. And that's an improvement on that 97.5%. And now what we can do is that part E where it asked about the probability of being less than or equal to 54. Now that's very easy to accomplish. We just go to Geogebra and type in 54, and it can find anything. 0.9599 is that probability. So with Geogebra, we can find all of these probabilities. The key is that getting set up, you just need to adjust the mean and standard deviation first for what kind of curve you're looking at, And then you can plug in all sorts of cutoff values for that bell-shaped curve to find areas. So let's do an example. We have here's a medical study, and they found a serum cholesterol levels, and it's normally distributed. So when you see normally distributed, what you can immediately do is imagine this bell-shaped curve. So we know we have something like this. It also tells us that when we go to Geogebra, we can use that normal distribution. And they tell us about this mean and standard deviation. So this curve we have for this random variable x, it's defined by this normal curve, mean of 1.75, and standard deviation 0.3. And with our bell-shaped curve, we can get a number line going. In the middle is always going to be our mean. And then we can make this number line using standard deviations below and above and removing by this 0.3. So this would be a 2.05, 2.35, and 1.45, 1.15. And this just helps give us an idea of what are likely values to come out and what are unlikely values to come out. So, a child has a cholesterol level of 2.11. What's the percentage of children in Wisconsin who have cholesterol levels that are higher than this child's? So we want to do with this normal curve that we're going to draw, and we have 1.75 in the middle. What we're going to do is have this cutoff value of 2.11, and we want to look higher, so we want to find this area to the right there. So that's essentially what we're going to do in Geogebra. So we're going to find this probability of x being larger than or equal to 2.11 using this mean of 1.75, standard deviation of 0.3. So if we go to Geogebra, what we'll need to do is adjust our mean. So our mean is 1.75. Standard deviation is 0.3, and we want this area to the right, so we're going to adjust to a right tail, and we want to find above 2.11. And why I like drawing that picture by hand first is so that when I plug into Geogebra, I should see the same exact thing that I drew. So since that picture matches up, I know it matches what I'm looking for. Make sure you hit enter, and we'll get that 0.1151. So that's our probability. So what this is saying is that 11.51% of children in Wisconsin have cholesterol levels higher than 2.11 milligrams per milliliter. Now, in terms of interpreting, do you think their parents should be worried? I mean, it's a low percentage. In terms of, is this an unusual value? Is this an unusually high? Let's go with that. Should they be worried in that, is this an unusually high value? Well, in terms of unusual, if we scroll back to when we first talked about empirical rule, it's going to be beyond 2 standard deviations away. Meaning with that 95% in the middle, there's this 2.5%, 2.5%. So it's not landing in the unusual region for this question. Especially if we go, too far. For our number line here, where 2.35 is 2 standard deviations above, 2.11 is somewhere within there. So it's not unusually high, although parents should probably always be worried about this. So statistically, no, but maybe in day-to-day, yeah. For the next one, find the percentage of children in Wisconsin who have cholesterol levels between 1.3 and 2.23. So what we're going to do is go to our bell-shaped curve. I'm just going to draw this picture first so that kind of double checks what I do in Geogebra. 1.3 is to the left somewhere, so we're going to have this lower bound of 1.3, upper bound of 2.23, which is somewhere over there. and we want to find this area in between. So we should be getting a fairly big probability out. So in GeoGebra, we're going to look at probability between 1.3 and 2.23, using our mean of 1.75, standard deviation 0.3. So we want to look between two values, lower bound 1.3, upper bound 2.23. And that picture looks similar to what I drew, and we are getting this large probability out of 0.8784. So that would mean 87.84% of children in Wisconsin have cholesterol levels between 1.3 and 2.23. So this is how, given a normal distribution, given a mean and standard deviation, we can find all sorts of probabilities given these cutoff values and using GeoGebra to calculate the probabilities for us.